In the previous activities, you built a solid foundation. You mastered the core vocabulary of cybersecurity, security, threat, vulnerability, risk, and you explored the three fundamental pillars that any security approach must protect: confidentiality, integrity, and availability. You even practiced identifying which pillar is attacked in real scenarios, and you created your own threat examples. Now it is time to move one step further and get acquainted with the most common threats that specifically target web applications. This is not an abstract exercise. Web applications are everywhere, from online banking to e-commerce platforms, from corporate intranets to public APIs. Understanding what attackers actually do, and how, is the first step toward being able to defend, test, and fix those applications professionally. This chapter presents the major web threats in plain language, with concrete examples. No deep technical jargon yet, but enough precision so that you can recognize each threat by name, understand what it does, identify which CIA pillar it affects, and remember it clearly for a quiz, and more importantly, for your future work as a cybersecurity and DevSecOps specialist. Injection attacks. Injection attacks are among the oldest and most dangerous threats on the web. The basic principle is simple. An attacker sends malicious data to an application, and that application mistakenly treats it as a command rather than as simple data. The most well-known variant is SQL injection, where SQL stands for Structured Query Language, the language used to interact with databases. Imagine a login form on a website. The application takes the username and password entered by the user and checks them against a database. In a vulnerable application, an attacker might type something like OR1 equals 1 in the username field. If the application is not properly secured, it may interpret this as part of a database query and return a valid login, without needing a real password. The attacker bypasses authentication entirely. SQL injection can be used to extract entire databases, delete records, modify data, or even execute commands on the underlying server. This attack directly threatens confidentiality. Data is stolen. Integrity. Data can be altered or deleted, and in extreme cases, availability. Data can be destroyed. Other types of injection exist beyond SQL. Command injection, where the attacker injects operating system commands, LAP injection, targeting directory services, and XML injection, among others. The common thread is always the same. The application fails to distinguish between legitimate user input and executable instructions. Cross-site scripting. Cross-site scripting, often abbreviated XSS, is a threat where an attacker injects malicious scripts, usually written in JavaScript, into web pages that will then be viewed by other users. The key point is that the attack does not target the server directly, it targets the users visiting the website. Here is a concrete example. Imagine a comment section on a blog. A user can type a comment, and that comment is displayed on the page for all visitors. If the application does not sanitize the input, an attacker could write a comment that contains a JavaScript script instead of normal text. When another user visits the page, their browser executes that script without knowing it. The script could steal the user's session cookie, a small file that keeps the user logged in, redirect the user to a fake website, or display a fraudulent form asking for sensitive information. Cross-site scripting primarily threatens confidentiality. Session data and credentials can be stolen, and can also threaten integrity if the injected script modifies what the victim sees on the page. There are two main variants: stored cross-site scripting, where the malicious script is saved in the database and served to all future visitors, and reflected cross-site scripting, where the malicious script is embedded in a link and only executes when a victim clicks that specific link. Cross-site request forgery. Cross-site request forgery is a threat that tricks an authenticated user into unknowingly sending a request on behalf of an attacker. The attacker does not need to steal credentials, they simply exploit the fact that the user is already logged into a trusted application. A simple example: you are logged into your online banking platform. In a separate browser tab, you visit a malicious website. That website contains a hidden image tag or form that automatically sends a transfer request to your bank, using your active session. Your bank sees the request as legitimate because it comes with your valid session cookies. The transfer goes through without your knowledge. This attack threatens integrity. Unauthorized actions are performed, and can threaten availability or confidentiality depending on what the forced action does. The defense against this type of attack involves using unpredictable tokens, called anti-cross-site request forgery tokens, that must be present in every sensitive request to prove it was genuinely initiated by the legitimate user. Broken authentication and session management. Authentication is the process of verifying who a user is. Session management is the mechanism that keeps a user recognized as logged in throughout their visit. When either of these mechanisms is poorly implemented, attackers can exploit the weaknesses to impersonate legitimate users. Common examples of broken authentication include applications that allow unlimited login attempts, enabling brute force attacks, where an attacker tries thousands of passwords automatically, applications that use weak or predictable default credentials, such as admin/admin, or applications that transmit passwords over unencrypted connections. Poor session management examples include session identifiers that are too simple and predictable, session tokens that never expire, meaning a stolen token remains valid forever, or tokens that are exposed in the URL, where they can be seen in browser history or server logs. This category of threat primarily targets confidentiality and can allow complete account takeover. If an attacker gains access to an administrator account, all three pillars, confidentiality, integrity, and availability, are at risk. Broken access control. Access control refers to the rules that determine what a logged-in user is allowed to see and do. Broken access control means these rules are either missing or incorrectly enforced. A concrete example: imagine an e-commerce platform where each user can view their orders at a URL like website.com/orders/12345. If the application does not properly verify that user 12,345 is the one logged in, another user could simply change the number in the URL to 12,346 and see someone else's orders. This technique is called insecure direct object reference. Other examples include a regular user who can access administrator-only pages by guessing the URL, or an application that enforces access rules only in the visual interface but not on the underlying programming interface, allowing an attacker to bypass restrictions by sending direct requests. Broken access control primarily threatens confidentiality, unauthorized access to data, and integrity, unauthorized modifications to data or system settings. Security misconfiguration. Security misconfiguration is one of the most widespread threats, and it often results not from a coding flaw but from a configuration error made by a developer, system administrator, or DevOps engineer. Default settings, incomplete setups, open cloud storage buckets, unnecessary services left running, or detailed error messages displayed to users, all of these are examples of misconfiguration. A classic example: a web server is deployed in production with its default configuration, which includes a publicly accessible administration interface protected only by the default username and password, admin/admin. An attacker finds this interface, logs in, and gains full control of the server. Another example: a web application displays detailed error messages when something goes wrong, revealing the database name, the version of the programming framework used, or even file paths on the server. An attacker uses this information to prepare a more precise attack. Security misconfiguration can threaten all three pillars depending on what is misconfigured and how it is exploited. Sensitive data exposure. Sensitive data exposure occurs when an application fails to adequately protect personal, financial, or confidential data, either in transit, while being sent over the network, or at rest, while stored in a database or file system. Examples include storing passwords in plain text in a database, so if the database is compromised, all passwords are immediately readable, transmitting credit card numbers over an unencrypted connection, allowing an attacker intercepting the traffic to read them, or storing medical records without proper encryption. This threat is directly linked to confidentiality. The key defense mechanisms include encrypting data at rest and in transit, using strong and modern hashing algorithms for passwords, such as bcrypt, and minimizing the amount of sensitive data stored by the application. Using components with known vulnerabilities. Modern web applications rarely start from scratch. They rely on third-party libraries, frameworks, plugins, and external components. When these components contain known security vulnerabilities and are not updated, the entire application inherits those vulnerabilities. A concrete example: a web application uses an older version of a popular open-source library to handle file uploads. A security researcher has already discovered and published a vulnerability in that version, explaining exactly how to exploit it. An attacker reads the public vulnerability report, checks which version the application is using, and executes the attack. This is why regularly updating dependencies and monitoring published vulnerability databases is a core responsibility in DevSecOps. Tools like software composition analysis scanners exist specifically to detect outdated or vulnerable components in a project's dependencies. Server-side request forgery. Server-side request forgery is a more advanced threat but increasingly common. It occurs when an attacker can manipulate a web server into making requests to internal systems on their behalf. Imagine an application that allows users to enter a URL, and the server fetches the content of that URL to display it, for example, a URL preview feature. If the application does not restrict which URLs can be requested, an attacker could enter an internal address, such as the address of an internal configuration service or a metadata endpoint on a cloud server, and the server would dutifully fetch and return that internal content to the attacker. This threat can expose internal infrastructure details, internal credentials, and sensitive configuration data. It primarily threatens confidentiality and can sometimes be used to pivot further into an internal network. Key takeaways. Here is a summary of the main web threats covered in this chapter, each linked to the CIA pillar or pillars it primarily affects. Injection attacks, such as SQL injection, confidentiality, integrity, availability. Cross-site scripting, confidentiality, integrity. Cross-site request forgery, integrity. Broken authentication and session management, confidentiality, integrity, availability. Broken access control, confidentiality, integrity. Security misconfiguration, confidentiality, integrity, availability. Sensitive data exposure, confidentiality. Using components with known vulnerabilities, confidentiality, integrity, availability. Server-side request forgery, confidentiality. Understanding these threats at this level is not just academic. As a future cybersecurity and DevSecOps specialist, you will encounter each of these in real applications. You will need to recognize them during penetration tests, understand what damage they can cause, know which pillar they threaten, and ultimately be able to propose or implement the appropriate fix. The next activities will build on this knowledge progressively, so make sure you are comfortable with each threat's name, mechanism, and real-world impact before moving on.